So let's continue our discussion by examining some stable metal alkyls. And we'll talk about why they are stable and what we can do to learn from their stability so that when we make other metal alkyls, we can have success in our synthesis. So let's examine this tungsten with the 6 methyl groups on it. Now, remember, the main degradation pathway for a metal alkyl is beta hydride elimination. Now, if we look at this complex, there are only alpha carbons, or alpha hydrogens on it. So, it's not possible to undergo beta hydride elimination because there are no beta hydrogens on it. That's the same case for this titanium complex too. So if we look, we have a benzyl group on here. So we have alpha hydrogens, but we have no beta hydrogen. And I will just quickly draw this ligand so that we can see that is the case. So here's a phenyl group, and if we look, that carbon right here, which would be in the beta position, does not have any hydrogens on it, so we cannot have beta hydrogen elimination. Similar case here. Well, this one does have beta hydrogens, but it's difficult to align this in a coplanar, in that correct orientation for it to react, just because of the steric bulk of this group. And then here we have something that does not have hydrogens on it. In fact, it has fluorines, and if you know anything about fluorine chemistry, the carbon-fluorine bond is extremely stable. And so it takes quite the special conditions in order to break that bond. So this is a stable metal alkyl in most cases. Down here we have hydrogens that are, yes, we have beta hydrogens, but they're kind of tied back. They're not easy to rotate around into the right position, and so this is less likely to beta hydride eliminate. Also, if you keep in mind, that carbon is a quaternary center, so it cannot do a 1-2 kind of elimination there because there's no hydrogen here to eliminate along with it. So that's another blocking of that potential pathway. Down here we have a very small ring, and it would be, one, very difficult to put a double bond anywhere inside this ring just because of the steric hindrance that we're experiencing. Because remember, when we put a double bond in there, we're going to change the bond angle, we're going to increase it. And so that's going to be a very strained situation. The other problem is the beta hydrogens are way over here, and that's actually more important in this case. And so it's just not available for the metal to react with those. And there's no way that these hydrogens can rotate or end up closer to where the metal is to be able to react that way. A very similar situation happens up here. This distance between the metal and the hydrogen is greater than what we would experience in the saturated version of this, in the ethyl group. And ethene has a 120-degree bond angle there. That places this farther away from the metal, making it much less likely to eliminate that hydrogen. Down here we have a different problem, whereas it's very similar to our case down here. The hydrogen is just very far away from the metal. Also, if we were to try to pull that hydrogen off and create a carbon with a quadruple bond into the other carbon, that just does not work. It doesn't happen. The orbitals are just not really lined up properly. So the product of that reaction is not stable, so that will not eliminate. Here, if we were to perform a reaction on this benzene ring, it would break the aromaticity of the ring, and that would be less stable, in addition to the fact that the bond angle is going to be difficult to interact with. Now, so far we've talked about kind of hiding away the hydrogens or eliminating the hydrogens access, or the metals access to the hydrogens. But what if we have available hydrogens? So here's an ethyl group, but we don't have any available cis open spots on the metal. And so here we have a ring that's coordinating to the metal, something like a porphyrin ring, or these could be relatively rigid. But the point is, all of the cis positions are occupied, and they're occupied with a very strongly bound ligand. So it's very unlikely for this ligand to come off of the metal, especially with that many attach points. And so the hydrogens over here on the beta carbon do not have an open position to interact with the metal. So this is just coordinatively saturated. So other ways that we can block alkyls from undergoing beta hydride elimination is if we have a D0 metal. Now, in order for beta hydride elimination to occur, there needs to be at least 2 D electrons available to bond with the hydrogen into the antibonding orbital on the hydrogen, and then the reaction can proceed. If there are no electrons in the D orbital, that cannot occur, and so we've stopped it at the beginning. Now you could still have kind of an allosteric interaction, which is where the hydrogen can have a little bit of bonding with the metal, but the metal will not be able to break the alkyl apart. So we'll still have a stable alkyl. We'll just have some other interactions in there. And then the other option is, instead of just completely coordinatively saturating the metal, we could just block the sites with very large ligands. So if we have a ligand that will block the beta hydrogens from interacting with the metal, just because it is that bulky, then we can stabilize a metal alkyl. So these are some of the ways that we can stabilize metal alkyls, and that way we can study them or use them in synthetic pathways. And these are useful to understand, and kind of a starting point for some of the organometallic reagents that we'll see later.